In this video, we will be going over some examples from the WileyPlus, talking about electric fields and how to solve for electric field based on different geometries. So, in this first question, this is very similar to the one that we did for our first week for electrostatics. So we have 4 particles arranged in a square. And I'm going to color code these. So what do we know about it? We know that our side length is equal on all sides, and that's 0.066 meters. We also know that we have 4 different charges. So Q1 is 7.24 nanocoulombs, and Q4 is negative 7.24 nanocoulombs. Additionally, we also have Q2 at negative 19.8 and Q3 at 19.8 positive. So we want to know the electric field measured from the center, which means we will need to find out what the separation distance is. So we're going to start with that. So our very first step, find separation distance. And when we do that, we know that each of our side lengths is equal to 0.066 meters. So now we need to find this. So this was this is 0.0933 meters. All right, but our separation distance is measured from the center, right? So the triangle that I just drew goes like this, right? But we want to find what that little purple length is. So we need to take half of our measured hypotenuse value, and we know that R is equal to 0.04667, let's just do 66 meters. All right, so I'm going to draw a diagram of how we can imagine our geometry and symmetry for this. It'll make it a lot easier to understand, a lot easier to solve our question. So first I'm going to draw our reactions from our 19.8, so negative 19.8 to Q2. So this is an attractive force, so that means it's going to be pointing to there at a longer length. And then it's going to be deflected from our 19.8. So that means it's going to be going that way from Q3. So these are the same magnitude because they are both 19.8. So this is Q2, and this is being deflected away from Q3. Now, taking a look at our 7.24, we know that we have an attractive force going to Q4, sorry, and a repulsive force from Q1. So I'm going to draw this a little bit better so you can visualize the magnitudes of the vectors. There we go. That's a little better. So this is attractive to Q4, repulsive from Q1. So on the top, we have 2 vectors of the same magnitude, but pointing in different directions, so that when we break it out into our x and y components, we know that our x components are going to cancel. Similarly, when we look at the bottom, we're going to see that our y components add and our x components cancel once again. So we're going to only consider y components. And since the magnitude of our y components is larger than that of the bottom here, going to be an overall upward force. So what we're going to need to do, we're going to take these in a positive direction. So we know that there's two of these in our positive direction, and then we're going to subtract our two negative direction y components. So let's draw what that looks like. Let's write out our equation. So electric field is going to be equal to, so we have two of these y components here, and we're using KQ2, and we know this is over whatever we solved for our separation distance squared. We know we also need the y component, so that's why we throw in a sine 45. And we know it's 45 degrees because it's a square. So that is for our upward force, and now we need to subtract our downward force. Let's use Q1 for 0.0466 squared. And then this gives us a final answer of 7.335 times 10 to the 4 newtons per coulomb. That is our final answer. So that's why it's important to understand the geometry and symmetry of some of these questions, because it's going to make them a lot easier to answer. So that is our first question done. Okay, next figure shows an arrangement of protons and electrons on a circular arc. So, which means all of these are going to have the same distance from the origin with all these different angles. So we have to find the magnitude and direction of the net electric field produced at the center, so at the origin. So we're measuring each of these from the origin. So some important things to consider. Consider that the electric field is the same for all. The electric field is same magnitude for all particles. And the reason why that is because protons and electrons both have an elementary charge of 1.6 times 10 to the negative 19 coulombs, and all that separates them is just their plus or minus symbol, right? So when we take electric field, we have our constant Q over separation distance. So that means all of these, when we measure them, are going to be equal, just we have to consider the different directions of them. So a lot of this will rely on sketching it out once again, but just know that each value, each measured value is going to be the same, right? Because we are going to be using just the absolute value of our charge. And our separation distance is the same because of the arc that they're arranged in. So I'm going to color code the crap out of this. And let's make it a little easier to understand. So I'm going to start with the left side. So measured from here, it's a positive charge, so that means we're going to be deflected this way. And this angle is the same as 4. It's our angle 4. Which means we have a positive x and a negative y component. Next, we have an electron. So that means we are going to experience an attractive force with a positive y component and a negative x component, where this angle is the same as this angle here. Right, next we have a proton. So that means we're going to have a deflective force And this angle here is equal to theta 2 plus theta 1, right? Because we want this whole arc here. Sorry, I gotta change this one too. Plus theta 4. It's almost done. We have, and this is going to have negative x and y components. For this next proton, it's going to be deflected, and this angle is theta 1, negative y and negative x component. And lastly, we have an electron, which is going to produce an attractive force solely in the positive x direction. So we're going to need a lot of different calculations for this. So that's why I've color-coded our work. So I'll see if I can start with this. So we're going to start off with calculating our electric field, because we knew that it was the same. And what we need to add, we just need to add our directions and our angles. So it's going to give us our separation is 0.0245. And that gives 2.396 times 10 to the negative 6 meters per coulomb. I'm just going to calculate again, make sure I'm not going crazy. Awesome. All right. So now we can get started. So we have to write out each of the x and y components for this question. So let's start with our red one. So E1x. So it's the positive x direction. So that's going to be then cos of, and then that's, oh goodness. So that's cos of r theta 4. Let's just write in our actual value for that. 4 is 34. Then our E1y, so we're in the negative y direction. So that's going to be negative E cos, E sine 34, sorry. Okay, next we have our second one, which is in negative x direction. And that is cos, it's 34 plus angle 3, 34, if I'm not mistaken. Yep. And then we have positive y direction, so that is positive sine 34 plus 34. Then for E3, in our x direction, we have negative y and negative x, negative E cos, let's see, and then that's 2 plus 1, angle 2 plus angle 1, so that's 32 plus 45. E3y, negative sine green one, it's E4 for x and E for y, both in negative directions again. So then that is for angle 1, so that's cos 32 and sine 32. And last but not least, we just have in our x direction for the fifth one, that's in the positive x direction, so that is just going to be E. So now we have to add up all of these components. So I'm going to go ahead and do that, and I'll come back when I'm done. Okay, so now that we added up all of our x and y components, now we can take the magnitude of it. So our magnitude is plus 9.137 times 10 to the negative 7. So our magnitude is our answer up here, 2.870 times 10 to the negative 6. So we take our magnitude, right, and we want to find our direction. So we were given a positive x sum and a negative y sum. So that means if we were to draw this out in a plane, it would put it about right here, and that's our angle. So we can find our angle by going tan inverse, and that's our x, that's EY. Over sum of EX, and that gives 71.433, and because it's measured clockwise, then that's where that negative comes in. All right, so that is question 2 done. A little bit of work. All right, so now for question 3. So this question also relies on our geometry a little bit. So we want to find the electric field produced at P given that it's surrounded by 2 curved plastic rods. So a couple things we can label. We know our distance from every point is 0.05 meters. Right, and now we want to draw some lines to indicate our geometry. So this is a repulsive force from our top half, right from Q plus. It's going to create lines going this way. And for our Q negative, we also have an attractive force, so then they're going to be pointing in the same way, radially, and so that means our net force is downwards. Net downward field. Sorry. So when we look at this one, we're going to have to use, it's kind of like the one previously, we have to use 2 of these values because we are accounting everything from our top half and our bottom half because they're pointing in the same direction. So if I were to write this out, so we have 2 of these, K, Q, separation distance, 0.05 squared. And so I'll draw out what this looks like. So since all of these are the same magnitude along this arc, if we were to draw the x and y components for these, we would see that our x components, since they point opposite, they're all going to cancel. So all x components cancel, right? So that just leaves all of our downward forces from our y components, all of it's going to be acting down. So that's why we need to add a sine value. And we are going to use sine from 90 minus negative 90. So you can consider this as if they were our integration bounds, right? So this is just so we include the whole circle, right? Because we want to use 90 from here and 90 from here. So when we solve for this, this is 2 times 8.99, 10 to the 9. Our charge is 0.4, 10 to the negative 12, which is our picocoulombs, 0.05 squared, and sine 90 is just, hold on, sorry, I think I did something. Sorry, I made a mistake. So from 90 to negative 90, right? So we're going to start with our sine 90. The minus minus 90 to plug in now. And then when we solve for that, electric field is 79.667 per coulomb. Okay, next question. All right, so this is like our notes example. We want to find our, we want to find what our electric field is at point P. And we know that since it's positive, it's going to be deflected from this point and deflected from this point. So our y components add, x's cancel out. So we can answer our first question. X components we know to be 0. So now all we need to do is solve for our y components. So when we took this, we found it to be 4 pi epsilon 0. And we had our charge over our separation distance. We can solve for that really quick. Square root of r squared plus l squared, l over 2 squared, I guess, right? Because this distance is l over 2. So let's write that in. Squared. And then we want our sine theta. So let's find sine theta. And that will be, so sine theta Opposite over hypotenuse. Opposite over hypotenuse. So let's see if I have room to add that. R squared plus L over 2 squared. Okay, so let's plug in our values and see what we get. So we have E equals 10 to the 9. This is Q. That's 8 times 10 to the negative 12 coulombs. This is square root squared. So square root squared, that means we could just kick out this square root radical. Just use... Actually, no, let's combine this and make this a little simpler. Let's put the R in there too. R is 0.07 meters. And then that way we can just do R squared. R is 0.07 squared plus half of 16 centimeters is 8 centimeters squared to the power of 3 over 2. And what does that get us? Let's find out. Times 8, 12 times 0.07 divided by 0.07 squared plus 0.08 squared power of 3 divided by 2. Right, and that gives 4.1911 newtons per coulomb. But we're not quite there yet because we've only solved for one of the upward forces. So then when we just multiply it by 2, that gives us 8.382. Okay, so not quite what we got up here. All right, but the method still stands. So maybe it might have been a little bit of a math error on my part, but that is how to solve that question for a line of charge. Okay, so our last question. Okay, so this one's going to be a little tricky. I'm going to need to check with my answer key quite a bit for this one. But this question is asking to find the ratio between an arc and a particle electric field. Let's see. Yeah, so by what factor is the magnitude multiplied? So that means we're going to have to take our E of our arc and E over our particle for our answer, right? So that means we're going to have to make two different equations. So let's start out with this one.